good morning. Welcome to a new lecture in detection, and in today's lecture we will be talking about performance of orthogonal modulation scheme, and then we will look into this bit level demodulation. Okay. So, let us get started, and as I have said, we will talk about this M array orthogonal modulation scheme. So, in this orthogonal modulation scheme we have one signal per orthogonal dimension. Okay. So, for example, this is the case of 3 array orthogonal modulation scheme. So, underlying orthogonal modulation scheme can be FSK, can be PPM, can be the orthogonal modulation realized using Walsh-Hadamard codes. So, whatever may be the kind of orthogonal modulation scheme, it does not matter. You can use the same framework to analyze these various modulation schemes in AWGN channel. Okay. So, what we notice here is we have 3 symbols, and these 3 symbols have equal energy, right. So, they are at the same distance from the origin. So, they will have the same energy. And secondly, we also notice that these symbols are at the same distance from each other, all right. So, let us say if the distance between the symbols is d, then every symbol is at a distance of d from each other, right. So, the first thing that we want to define when we are talking about this modulation schemes is the power efficiency, right. We have started looking into the power efficiency of various modulation schemes like COM, PSK and PAM in the last lecture, and today we will be looking into this power efficiency of orthogonal modulation schemes. Okay. So, what is power efficiency? It is d square by EB, and what is d in this case? If this distance is a, d will be simply root 2 a. And what is EB? EB as always is Es by log 2 m. Okay. So, power efficiency we have got is root 2 a square times log 2 m divided by Es. And what is this Es? A symbol energy. Es is simply a square. Okay. So, what we will get is the power efficiency is 2 times log 2 m, and this power efficiency is very different from the power efficiency that we got in the case of COM, PAM and PSK. What happened in the case of power efficiency there? There the power efficiency decreased with m, here the power efficiency increases with m. Thus, as you increase the order of modulation, the modulation schemes becomes more and more power efficient. Okay. And that is why we like these orthogonal modulation schemes to be used in the power efficient channel. Okay. So, let us look at some kind of numbers. So, if you double m, so increase m from 2 to 4 to 8 to 16, 32, 64 and 1024, power efficiency increases by 2. Okay. So, for every double increase in m, power efficiency increases by 2. And you can also express this power efficiency in dB scale, and this power efficiency in dB scale will help you to quickly calculate the Abno requirement for a given symbol array rate performance. For example, we have seen that in case the power efficiency was 4, the Abno requirement was 12 dB at a bit error rate of 10 to the power minus 8. So, now I can easily calculate the Abno requirement if my orthogonal modulation is 8 array orthogonal modulation. If I am using m as 8, my power efficiency is 6, in dB it is 7.8. Thus, the Abno requirement will decrease by 1.8 dB. So, it will go from 12 to 10.2. Of course, this is not very precise, but these numbers will help you arrive at quick estimates of Abno requirements. Okay. So, you can see that if you increase this m to 1024, you can have a 10 dB gain when you go from 2 array orthogonal modulation scheme to 1024 array orthogonal modulation scheme, and this will reduce the Abno requirement also by 10. So, if for 2 array orthogonal modulation scheme you require 15 dB Abno, for 1024 array orthogonal modulation scheme you will typically require somewhere around 5 dB. Okay. What is the main message in here? The main message is the calculation of this power efficiency is really trivial, it is easy, right, it is simply 2 log 2 m. So, if you know the Abno requirement for a certain array orthogonal modulation scheme, from that you can derive the Abno requirement for any other array orthogonal modulation scheme, and that is why we love this power efficiency. Okay. So, it will also be helpful to show you how does this power efficiency in dB scales with m. Okay. It increases logarithmically. All right. Now, the question is, so we now know that if m increases, power efficiency increases, Abno requirement decreases. So, what happens if I increase this m to infinity, right? What will be the Abno requirement in that case? And the first thing that we will see in this lecture is that Abno requirement will drop to somewhere around minus 1.59 dB if you have m as infinity. So, what we are saying is, we will show in this lecture, as m tends towards infinity, the Abno requirement drops to as small as minus 1.59 dB. And actually this is the Shannon's limit that we have seen before. So, Shannon predicted that if you have infinite bandwidth in the channel, then the Abno requirement can be made as small as minus 1.59 dB. And we will see today that these orthogonal modulation schemes also requires an Abno of minus 1.59 dB if you have m tending to infinity. Okay. Let's see how this number can be derived using Shannon's idea. So, we have seen this equation before. I guess when we first time looked into this orthogonal modulation schemes, we said that Abno should be greater than SNR divided by log 2 1 plus SNR. When m tends to infinity, these orthogonal modulation schemes begins to require infinite dimensions, thus they will have infinite bandwidth requirement. When bandwidth tends to infinity, the SNR approaches 0 because noise power becomes infinite as well. And thus to think about this, so when SNR tends to 0, this is 0 log 2 1, which is 0. So, this is 0 by 0 form, and you have to arrive at this quantity in the limiting sense, and you can use L'Hopital. Okay. So, if I express SNR as x and I want to write log 2 as ln divided by ln 2, so actually this is this, and then I can take the limit as x tends to 0. When x tends to 0, I have to differentiate both numerator and denominator. When I differentiate numerator, I get ln 2. When I differentiate denominator, I get 1 upon 1 plus x. Now, I can substitute x as 0 and I get Abno requirement as ln 2, which is minus 1.59 dB. Okay. So, this follows from Shannon's basic equation, and we will prove in today's lecture that orthogonal modulation schemes also requires the Abno of minus 1.59 dB if you assume that m is tending to infinity. Okay, so let us start looking into the performance of these orthogonal modulation schemes. So, what we assume is that we have m hypothesis. So, we can use the capital letter M instead of small letter m. So, we have m hypothesis and we have a signal set, where these signals are assumed to be of equal energy, and because we want to use this ML detection rule, we also assume that these signals have equal priors. Okay. So, this signal S1 corresponds to hypothesis 1, signal S2 corresponds to hypothesis 2, signal SM corresponds to hypothesis M. So, we have M hypothesis and we have M signals. Okay. Now, let us look at this receiver structure that we will require to detect these M orthogonal signals, and receiver structure would be same as the receiver structure that we have seen in the case of M array detector. So, the receiver structure that we have seen when we looked into this M array detector can be used for any modulation scheme whatsoever it is. So, it can be used for PAM, COM, FSK, PPM whatsoever. That was a generalized receiver structure. So, the receiver structure will be same. So, a receiver signal which in this case is S1 plus n. So, we are assuming that the first hypothesis is transmitted, first hypothesis has a signal S1, and then what we do in this receiver? We take the inner product of the received quantity with all signals in the signal set, and then once you have computed this inner product, you have a block which select the hypothesis which has the largest resultant at this point. And what we also show here is that at these points we have M random variables Z1, Z2 and Zm. Okay. So, look at this receiver structure again. So, we are assuming that the signal that is arriving is S1 plus n, then we compute the inner product of this received value with all signals in the signal set, and then we decide upon the hypothesis where we have the largest output. So, if in this branch we have the largest output, we select the hypothesis as 1. So, when we discuss this M array detector, we had this bias also at this point, but now we have got rid of this bias. Why is that? So, remember that this bias looked something of this form. This term in the bias dealt with the signals which are with different priors, and because we are assuming all signals have the equal a priori probability, this term is 0, and if we assume that all signals have equal energy, then this term is also relevant. So, we do not have to use any bias in the case we have signals with equal energy and equal probability. So, we should not be using bias, and that is why for this M array orthogonal modulation scheme we are not using this bias. Other than that, this receiver structure is exactly similar to the receiver structure that we discussed in the case of M array detector. Okay. Now, before we can dig our teeth into this probability of error formulation, let me revise some basic stuff. Okay. So, what we need to do is we need to find out the mean and variance of these random variables. So, these random variables that we have in here, we have to find the mean and variance of these random variables. What will be the probability density function of these random variables? The probability density function of these random variables will be Gaussian, because any linear functional of a Gaussian noise is a Gaussian random variable, is not it? So, at this what we are having is a linear functional of a Gaussian noise. So, all these random variables will be Gaussian random variable, and thus what remains is to identify what is the mean and what is the variance. Okay. So, this we have to see. You must be an expert in finding out mean and variance by now, but let us do it. Okay. So, what we are assuming that we are receiving S1 plus n, and we are finding out the inner product with the signal Si, and that is giving us this random variable Zi. Okay. So, you know that inner product is bilinear operation. So, you can compute this by computing the inner product of S1 with Si plus inner product of noise with Si. Let us see what happens when I is 1. So, we will get Z1, and Z1 is simply the inner product of S1 with S1 plus inner product of noise with S1. And what is the mean of this random variable? Mean of this random variable corresponds to simply norm square of S1. This term does not have any mean, this mean is 0 because the mean of noise is 0, and hence mean of Z1 is simply norm square of S1, which is simply the energy of a signal or a symbol, and which we call as m, okay, just for simplicity. So, remember the mean of this random variable is simply Es or symbol energy. What happens when I is not 1? When I is not 1, we have Zi, which is the inner product of S1 with Si plus inner product of noise with Si, and this is 0 because the signals are orthogonal signals. Okay. So, what we are left with is inner product of n with Si, and what is the mean of this? Mean of this is 0 because noise has 0 mean. Okay. So, in short we can conclude that mean of Zi is energy of a signal if I is 1, and for all other i's it is simply 0. And also remember, because we will be using this shortly, that norm square of S1 is Es, symbol energy, and symbol energy is always bit energy times number of bits in a symbol, and number of bits in a symbol is log to m, and we call this thing as m. Okay. Now, what remains is to find out the variance of these random variables, and to think about variance we can start thinking about the covariances, and here we are taking the covariance of Zi with Zj, and you know that you have to write first Zi and Zj, and you have to take the covariance. Covariance we have seen is not influenced by constants. This is a constant term. Okay. This is a constant term. So, you can better remove these constants, and thus this covariance reduced to this covariance. So, here we are finding the covariance of inner product of n with Si with inner product of n with Sj, and we have solved this several times in this course. This is simply n naught by 2 if I assume that the one sided power spectral density of input noise is n naught, and if it is white Gaussian noise, because we always assume input noise to be white Gaussian noise with one sided power spectral density of n naught, and so is here. So, this covariance is simply n naught by 2 times inner product of Si with Sj, and we know that this will be 0 if j is not same as I, and thus to have this effect we have an impulse function here which is 0 if I is not same as j, and it is 1 if I is same as j. So, we are saying that this thing is simply sigma n square times an impulse function. Okay. We will see what is the sigma n square now. So, from this we can find out the variance of Zi, which is covariance of Zi with Zi, and we have seen that this will be sigma n square. Delta impulse function is 1 if j is same as I. So, this is just sigma n square, and this will be n naught by 2 inner product of Si with Si, and inner product of Si with Si is norm square of Si. So, we have got sigma n square is n naught by 2 times Es, energy of the signal. Okay. Okay. So, what we have got is we had this bunch of Gaussian random variables, and we have seen that all these random variables have the variance of n naught by 2 times Es, and what we have seen is that this random variable has got a mean of Es, and all other random variables have got a mean of 0. And now, we can easily calculate the probability of error for this orthogonal modulation scheme. Okay. Let us get started. So, here what we are trying to do is we are trying to evaluate probability of being correct when hypothesis 1 is transmitted. Okay. So, let us use H instead of M. So, in this we are evaluating what is the probability of being correct if first hypothesis is transmitted. Okay. And from here we can easily derive what is the probability of being correct overall, right, because all these signals that we have are the signals with equal energy, all the signals have the same distance from all other signals, and thus there is no reason why noise will favor one signal over another. All signals will see the same error probability, and thus on average the error probability that you will see will be the error probability corresponding to one hypothesis being transmitted. So, that is the big plan that we are having here. Okay. So, we simply calculate what is the probability of being correct if first hypothesis is transmitted, and from here we can find out the average probability of error. Okay. So, given that we have transmitted hypothesis 1, what would you like to have? You would like to have that the numerical value corresponding to random variable Z1 should be the largest, because when the numerical value corresponding to the random variable Z1 will be the largest, your detector will choose the hypothesis to be the first hypothesis. Okay. So, that even corresponds to the probability of being correct. So, what we want is, if we assume that this random variable has a numerical value small z1, then what you want to have is that this z1 is the largest. So, what you want to have is this random variable takes in a numerical value small z1 and all other numerical values corresponding to all other random variables should be smaller than z1. Okay. So, z2 which corresponds to the numerical value of random variable z2 should be less than z1, zm which corresponds to the numerical value of random variable zm should be less than z1, and so on and so forth. Okay. And what is the condition on numerical value z1? This can be any number from minus infinity to plus infinity. Okay. So, if this condition is satisfied, the receiver will make a correct choice. Okay. Let us see how can we solve this up. So, first we have to find what is the probability that random variable z1 takes in a value around small z1. It is not exactly z1, because that probability is 0, right. If you have a continuous random variable, probability that a random variable will pick on a specific value is 0. So, we do not talk about probability of this random variable taking a numerical value z1, but what we want to find out what is the probability that this random variable takes in a value around z1. That means between z1 plus delta and z1, okay, delta being very small, and this probability you can find easily by multiplying the PDF of this random variable z1 with a small delta, which in this case is dz1. And how do we find the PDF of z1? It is simple, it is a Gaussian random variable, just you have to plug in the mean is m, and the variance we have calculated is sigma n square. Okay. So, this will give us the probability that random variable z1 will take in a value around z1. And now, to this we have to multiply the probabilities of all these events, and all these events are independent events, and thus we have to simply multiply the probabilities of these events. Okay. So, you have this multiplier which simply multiplies the probability corresponding to each event m minus 1 time, is not it? And what is the probability of each event? So, let us focus on, let us say, this event. So, here we have to find out what is the probability that random variable z2 takes in a value less than z1, and this can be obtained by integrating the PDF of Z2 from minus infinity to Z1, and this is exactly what we are doing in here. We are integrating the PDF from minus infinity to Z1, and the PDF is the PDF of a Gaussian random variable which has got a mean of 0 and the variance of sigma n square, okay. And all other terms will have the same product, okay. So, you simply take this term and you multiply this m minus 1 times, okay. So, this thing will give you probability of being correct if you have transmitted the hypothesis as 1. And what you can also recognize in here before we move to next slide is all these terms have the same contribution. So, we can also simply write this in this way. So, each term has this contribution and we have to simply multiply this m minus 1 times, that is it, everything else remains same here. Now, what we want to do is we want to express this thing in terms of Q function. We know that this is the probability that Z2 takes in a value less than Z1, and this is 1 minus probability that Z2 takes in a value greater than Z1. And we know how to work this out. This is Q Z1. What is the mean of Z2? It is 0. What is the variance of Z2? Sigma n square. So, what is the standard deviation? It is sigma n. So, we know that this thing is simply 1 minus Q of Z1 divided by sigma n. Now, we can have this instead of this in here, and we get to this expression. Okay. Now, we make a trivial change in variables. We say that Z is simply Z1 by sigma n. Okay. So, we have defined Z to be this. So, before thinking about this, let us look at this slide first. I am trying to find out this ratio m square by sigma n square. M square is Es square, sigma n square is n naught by 2 times Es. So, m square by sigma n square is 2 Es by n naught, and Es is Eb log 2 m. So, m square by sigma n square is 2 Eb log 2 m by n naught. M by sigma n is the square root of this thing, which is the square root of 2 Eb by n naught times the square root of log 2 m, and we define A as the square root of 2 Eb by n naught just to simplify our notations. Okay. So, we have got that m by sigma n is A times root of log 2 m, where A is square root of 2 Eb by n naught. Now, let us look at this again. So, what we are trying to do is we want to write this as Z1 by sigma n minus m by sigma n whole square by 2. So, look at just this term. Instead of it, we want to write it like this: Z1 by sigma n, we defined it to be Z, and m by sigma n, we have defined it to be A times root of log 2 m. So, this simply becomes this: Q of Z1 by sigma n is simply Q of Z, and dZ1, what is dZ1? dZ1 is dZ times sigma n, and thus this sigma n gets cancelled. So, what we have got is probability of being correct if we have sent the hypothesis 1 is simply this integration. From this we can easily calculate the probability of error, which is 1 minus probability of being correct. Okay. And we have already calculated that probability of being correct is this thing. So, probability of being in error is this thing. What more we have done is we have introduced this phi of z, where phi of z is simply 1 minus q of z, okay. And a in this expression is root of 2 E b by n naught. Whereas, if you use this MATLAB and if you carry out this integration, you can get precisely the probability of being in error if hypothesis 1 is transmitted, but this is also the overall probability of being in error, because probability of being in error is simply the probability of being in error if hypothesis 1 is transmitted plus probability of being in error if hypothesis 2 is transmitted, so on and so forth, plus probability of being in error if hypothesis m is transmitted divided by number of hypotheses. And if all this probability of error are same, then the overall probability of error is also simply the probability of being in error if hypothesis 1 is transmitted. Okay. So, thus this also gives us the average probability of symbol error. Okay. We are not yet done, because what we want to do is we want to think about what happens to this probability of error if m tends to infinity. That is the question that we like to ask. Also, obviously, this is also an important result, because this gives you probability of error of any orthogonal modulation scheme. Okay. But we are trying to wonder about another question also in here, that what is the probability of error if m tends to infinity. Okay. To think about that, let us confine ourselves to probability of being correct, and we have said that probability of being correct is this thing. Now, we make another change in variable. We say that z minus a under root of log 2 m is x. So, probability of being correct is simply this thing. So, we are replacing this giant expression simply by x square by 2, and this z thus becomes x plus a root of log 2 m times m minus 1 dx. Why we are doing this? Because we want to handle all terms containing m at the same place. Okay. So, here it had a term containing m, we have shifted this to this side. So, now only this term has the terms containing m. Okay. So, the question that we want to ask is, what is the probability of being correct if m tends to infinity? Okay. So, you have to ask this question in limiting sense. So, you want to make m tending to infinity, and you have to solve this limit. So, what we want to do is we want to define this as a when m tends to infinity, this quantity as a when m tends to infinity, and so ln a is simply limit when m tends to infinity ln of this quantity. We will first try to see how does this a behaves when m approaches infinity, and then we will plug in this value of a in this expression, and then we will see how the probability of being correct behaves with m tending to infinity. Okay. So, that is the goal of this exercise. All right. Okay. So, if m tends to infinity, m minus 1 is same as m. So, from here we can get to this simple, and now we can also bring this m to this side, and so that limit is simply this, where instead of writing m I have written it as 1 by m, okay, for some strange reasons that will become clear now. And let us see what is this limit as m tends to infinity. So, when m tends to infinity, this is 0, when m tends to infinity, I have ln phi of infinity. What is ln phi of infinity? What is phi of infinity? Phi of infinity is 1 minus q of infinity. What is q of infinity? Is 0. So, this is 1 minus 0. Phi of infinity is thus 1, and what is ln 1 is 0. So, this limit is of 0 by 0 form, and thus to solve this limit I have to use L'Hopital. Okay. So, first I define two functions. So, I take in this numerator. So, f1m is the numerator and f2m is the denominator of this expression. Then ln a is limit when m tends to infinity, derivative of f1m divided by derivative of f2m, and now you take in the derivatives and you hope that you get a neat thing. Okay. Okay. So, then we are differentiating this f1m, and you do not need a lot of skill to differentiate this. So, ln x has a differentiation 1 by x. So, this terms becomes 1 by this, and then you have to differentiate the argument of this thing. Okay. And before differentiating the argument of this thing, you have to use this identity which will make things easier, that phi of x is 1 minus q of x, and q of x is e to the power minus x square by 2 if x is pretty large. We have used this property several times. So, phi of x is simply 1 minus e to the power minus x square by 2. So, phi of this thing is simply 1 minus e to the power minus x plus a root of log 2 m square divided by 2, and you have to differentiate this term with respect to m. Okay. And this thing will give you derivative of f1m. Now, let us first deal with this term. When m tends to infinity, this term is 1. So, we do not have to worry about this. Okay. So, we can replace this simply by 1 and get rid of it. And now, what remains is the derivative of this quantity, and I will not explain the derivative of this because anyone can do this. You can look at this slide. Here I have carried this derivation, but what you can get in the end is that this is simply of this form b into m to the power minus 1 times e to the power minus a square by 2 times log 2 m, where b contains all coefficients that are not function of m. We are trying to evaluate this limit as m tends to infinity. So, whatever terms which are not containing m are really not relevant. Okay. What you might notice at this point here though is that b is some positive constant. Okay. So, f1 dash of m is simply this. Now, what I can do is I can write this log 2 m as ln m by ln 2. So, instead of this I can write it like this, trivial, and instead of thinking about this I can think about this quantity, because I know exactly what it is. This is simply m to the power minus a square by 2 ln 2. So, f1 dash m becomes b times m minus 1 times m to the power minus a square by 2 ln 2. So, this is what we have here, and thus I can write f1 dash m as also b times m to the power minus 1 minus a square by 2 ln 2. What was f2m? f2m was really simple, 1 by m. So, this derivative is simple, minus 1 by m square. Now, what is this ln a? ln a is limit when m tends to infinity, f1 dash m divided by f2 dash m, and this if you work out, So, we have seen that this is b m to the power minus 1 minus a square by 2 ln 2, and that was minus 1 by m square. So, we can have m square here. So, this is simply minus p m to the power 1 minus a square by 2 ln 2, okay, this thing. Now, you can see that if 1 minus a square by 2 ln 2 is a positive quantity, then what you have is infinity raised to power a positive quantity, which is infinity. This thing is infinity, and because of this minus, it will be minus infinity. Okay. So, if this 1 minus a square by 2 ln 2 is greater than 0, then ln a is simply minus infinity, and if this thing is less than 0, then you have infinity to the power less than 0. That means you have infinity raised to something negative, and this is simply 0. So, in this condition ln a is 0. What is this a square by 2 ln 2? A square, if you remember, we have defined it to be as 2 E b by n naught. So, a square by 2 ln 2 is simply abno by ln 2. So, instead of writing this, I can write it like this: ln e is minus infinity if abno is less than ln 2, ln a is 0 if abno is greater than ln 2. From here I can say that a is 0 if abno is less than ln 2, and a is 1 if abno is greater than ln 2. Okay. Now, let us put this a back into this probability of being correct. So, probability of being correct was this: if abno is less than ln 2, then a is 0, and probability of being correct is also 0. If abno was greater than ln 2, then a was 1, and then it is an integration of PDF from minus infinity to plus infinity, which is also 1. So, what we have got is, if abno is less than ln 2, then the probability of being correct is 0, and if abno is greater than ln 2, then the probability of being correct is 1. Okay. We can write it like this as well, that probability of being correct is 0 if abno is less than 0.69. The probability of being correct is 1 if abno is greater than 0.69, ln 2 is 0.69. And you can also express this in dB, which is usually done most of the time. So, we have got to this expression that probability of being correct is 0 if abno is less than minus 1.59 dB, and probability of being correct is 1 if abno is greater than minus 1.59 dB. And this proved what we were talking about, that if you have m tending to infinity, that means if you have infinite bandwidth available, so that you can have m array orthogonal modulation scheme where m tends to infinity, then the abno requirements drop down to minus 1.59 dB, okay, and this is an important result. So, do we have to live with this such complicated probability of error and probability of being correct formulas? No, you also have union bound in this case. Union bound is same as intelligent union bound, is same as nearest neighbor approximation for orthogonal modulation scheme. Okay, this is one and the same thing, both leads to the same result, right, because all signals are equidistant from each other. Thus, the number of nearest neighbors is m minus 1, q of square root of eta p abno by 2, eta p we know is 2 log 2 m. All right. So, you can substitute this eta p 2 log 2 m in this, and you can write this as this, and this is also E s, is not it. So, what you can say that probability of being correct is less than or equals to m minus 1 times q of under root of E s by n naught. You can use any expression whatever you want. So, here we show how the probability of error behaves with EBNO. Again it follows a waterfall decrease, and you can see that as m increases, the EBNO requirement decreases for a bit error rate of 10 to the power minus 8. But of course, you are still very far from the Shannon's limit. Okay. So, m that is required must be pretty large, all right. And from this curve you can also see that the quick estimates that we had are really precise, very close. Okay. So, you can use quick estimates to find out whether your simulation models are correct or whether your calculations are correct, and or you can use the precise formula that we have used to get to these probability of error curves. So far we have looked how to calculate the symbol error rates for various modulation schemes, and now it is the time to look at the bit error rates for these modulation schemes. And going from the symbol error rates to bit error rates is really simple. Okay. So, that is what we have to do. What happens when you want to identify the bit error rate performance for these modulation schemes. Okay. So, let us start with example, and as always I will like to start with this 4-com as the running example. Okay. So, here we have 4 symbols S1, S2, S3 and S4. All these symbols are at a distance of t and they have the equal probability and things like that. Okay. Now, what has changed in this diagram, if you notice carefully, is also we have labeled what are the bits corresponding to these symbols. Okay. So, symbol S1 has this bit 0 0, symbol S2 has the bits 1 0, symbol S3 has the bits 1 1, symbol S4 has the bits 0 1. And what you can also notice is that there is only a 1 bit difference between the bits of the neighboring symbols. For example, this differ only by 1 bit if you compare this with this. Okay. If you compare this with this, there is only a 1 bit difference. If you compare this with this, of course, there is a 2 bit difference. So, what we are saying, the nearest neighbors have only 1 bit difference if I am using what is known as gray coding. This is a gray coded bit map which makes sure that nearest neighbors differ only by 1 bit. Okay. And we have to find out what is the bit error rate if I am using this gray coded bit map. This bit I am saying as B1 and this bit, the second bit, I am saying as B2. And again same as before, I am assuming that hypothesis that we have transmitted is S1, and as before we assume that the noise that rides on this S1 is NC in the in phase direction and N is in the quadrature direction. Okay. So, probability that bit 1 is 1, given that we have transmitted 0 0, will create an error. This is the probability that this bit is in error. And when will this happen? This will happen either if you consider this signal S2 or you consider this signal S3. So, these two signals have their first bit as 1. So, this event will happen when NC will become less than minus d by 2. So, this distance is d. If NC becomes less than minus d by 2, then the received value will lie to the left of this axis, and then either you will have S2 or S3, and both these symbols have their first bit as 1, and that will make the first bit to be 1 if you are transmitting signal S1. So, this event corresponds to the probability of NC being less than minus d by 2, and this we know by heart is simply q of d by 2 sigma. Easy. So, now we have to find what is the probability that bit 2 is 1 given that you have transmitted 0 0. That also corresponds to an error situation, and this is probability that ns is less than minus d by 2, because when this happens either you have signal S4 or S3 and both signals have the second bit as 1. Okay. So, probability that your second bit is 1 is when ns is less than minus d by 2. All right. So, probability that second bit is 1 is simply probability that ns is less than minus d by 2, and this is also q of d by 2 sigma. The overall probability of bit error is simply q of d by 2 sigma, okay, and which is q of root of eta p abno by 2. And remember, these bit errors are independent. Okay. So, this bit error does not depend upon this bit error, or this bit error does not depend upon this bit error, and that is why these probabilities simply add. Now, let us reinforce our understanding by looking into different example. So, the underlying modulation scheme remains same. However, we have assigned the bits to the symbols using what is known as lexicographic coding or lexicographic bitmap. Okay. So, this symbol is assigned 0 0, this is 0 1, this is 1 0, and this is 1 1. Now, you see that these neighbors differ by 2 bits, and that is bad, this we will see. Okay. So, again same, we have to find what is the probability that bit 1 is 1 given that you have transmitted 0 0. So, this bit becoming 1. So, either you have 1 here or 1 here, and this will happen when ns is less than minus d by 2. This is simply q of d by 2 sigma, and then we have to find what is the probability that bit 2 is 1 given that you have transmitted 0 0. And when will this happen? This will happen when either you have this or you have this situation. So, either your received value lie in the 4th quadrant or it lies in the 2nd quadrant. So, this will lie in the 4th quadrant when NC is greater than minus d by 2. That means that you lie to the right of this axis, and when ns is less than minus d by 2, that means you lie below this axis. So, you remain in the 4th quadrant. Similarly, this event will correspond to the received observation lying in the 2nd quadrant, and that will give us the probability that bit 2 is 1. Okay. Now, we can solve this easily. So, first let us appreciate that this probability will be going to be same as this probability, just the names of the random variables are different. If these random variables have the same mean and the same variances and the same distribution, these two probabilities will be same, and thus we have a factor 2 in here. This probability is simply q of d by 2 sigma, this we have seen before, and this probability is q of minus d by 2 sigma. Okay. And so, you can also write that q of minus d by 2 sigma as this, and you multiply this with this, you get this, multiply this with this, you get q square function, and approximately you can find that probability of bit 2 being 1 is 2 times q of d by 2 sigma. Of course, we are assuming that hypothesis 1 is transmitted. So, what is the overall probability of being in error? Okay. So, there are 2 bits, number of bits is 2, probability of first bit being in error is this, probability of second bit being in error is this. The overall probability of error is this plus this divided by 2, which is this. So, what we have got in lexicographic coding, you have got probability of bit errors 3 by 2 times q of d by 2 sigma. So, this is factor 1.5 times larger than the bit error that you have got in gray coding approach. So, though it is not a proof, but it of course conveys the idea that gray coding should be used while assigning the bits to the symbols. Okay. Okay. Now, we go and see how to evaluate this bit error rate using this nearest neighbors approximation that we have used for calculating the symbol error rate as well. And remember, this nearest neighbors approximation states that probability of symbol error rate can be approximated by multiplying the number of nearest neighbors with the skew function. Okay. BER is an important word. BER stands for bit error rate. Okay. So, sometimes we call this as probability of bit errors or simply bit error rate, all right, BER. Now, if we assume that we are using gray coding, what we assume also is that these nearest neighbors only differ by 1 bit, because we are using gray coding. Now, when we are using this expression, it simply means that the error happens mostly when a symbol slips to one of its neighbors. Okay. Symbol is most likely getting confused by its neighbors. Okay. So, symbol error rate happens when the symbol slips to one of its neighbors' decision region. So, bit errors will also happen when a symbol is slipping to its neighbors' decision regions, and if the symbol slips to its neighbors' decision regions, and if we are using the gray coding mechanism, that means whenever a symbol slips to its neighbors, 1 bit error happen. Okay. So, if this X symbol errors happens, and if these errors are mostly by symbol slipping to its neighbors' decision regions, then X symbol errors corresponds to X bit errors, because neighbors only differ by 1 bit. If we are transmitting Y symbols, that means we are transmitting Y log to m bits, because per symbol there is log to m bits. Okay. So, what is the bit error rate? Bit error rate is how many bits in errors divided by total number of bits. Okay. So, X divided by Y log to m. I can write this as 1 by log to m times X by Y. And what is this X by Y? It is the symbol error rate. How many symbols in errors, X symbols in errors, how many symbols transmitted, Y symbol transmitted. So, X by Y is symbol error rate and PB is bit error rate. So, bit error rate is simply PE divided by log to m. Okay. So, we have got a neat relationship between bit error rate and symbol error rate if we are using this nearest neighbors approximation. Okay. This relation cannot be used when we are trying to estimate the bit error rate in terms of symbol error rate for orthogonal modulation schemes. This relationship works fine for COM, PSK, PAM and so on and so forth, okay, but not when you are using orthogonal modulation schemes. Let us see the idea that is in here. Let us assume that in a symbol I have an n bit sequence. That means I have 2 to the power n symbols, and if I have an n bit sequence, let us say I am having 4 bit sequence, and when I am using this orthogonal modulation schemes, remember this picture, all symbols are at equal distance from the considered symbol. Thus, this symbol might slip to this symbol might slip to this symbol, and so on and so forth. And thus, in this orthogonal modulation scheme, what happens is there is nothing like gray coding, because all symbols are neighbors of a considered symbol, and thus you cannot make sure that the neighbors only differ by 1 bit. That is not possible. Okay. And that is why you cannot use this idea of nearest neighbors approximation and gray coding that we use to derive this relationship. Okay. Now, so what we have seen is if we have transmitted this symbol might slip to any other symbol. All symbols are equally likely to get confused with, and thus I can slip to any of these m minus 1 symbols, any, right. On an average I will like to slip to each symbol one time. Now, let us see how many symbols differ by 1 bit. If there are n bits in a sequence, the number of symbols that differ by 1 bit compared to the considered symbol is NC1. For example, if I have 4 bits and this is the symbol that I have transmitted, if you have to find out how many symbols differ by this symbol in 1 bit, then there are 4 symbols. So, you can have 0, 0, 1, 1. So, this symbol differs by this symbol in this bit. You can have 1, 1, 1, 1. This symbol differs by this symbol in this bit. You can have this. So, this symbol differs by this symbol in this bit. You can have this. So, this differs by this in this bit. So, if I have a 4 bit sequence, you have 4 symbols which are different from this symbol in 1 bit, and that is NC1. Similarly, you can ask the question how many symbols differ by the considered symbol in 2 bits, NC2. Similarly, you can ask the question how many symbols differ by n bit compared to the considered sequence, NCN. So, from this basic simple idea, you can find average number of bits in error in m minus 1 symbols. So, NCI symbols will differ by I bits, and you can find out the average number of bits in error by running this I from 1 to n. And this series is well known. This is simply n times 2 to the power n minus 1. If you know this, you can easily calculate the average number of bits in error per symbol by simply dividing this thing by m minus 1. And remember, 2 to the power n is m. So, this is simply n m divided by 2 divided by m minus 1. Okay. So, this is average number of bits in error per symbol. So, if there are x symbol errors, we will have these many bit errors, and if we transmit y symbols, we are transmitting n times y bits. So, similarly, bit error rate is this thing divided by this thing. So, this is the number of bits in errors divided by total number of bits transmitted, and again we can rearrange this. So, this n cancels with this n. So, we have m 2 m minus 1, and we have x by y, which is symbol error rate. So, we have got a relationship between bit error rate and symbol error rate for orthogonal modulation schemes as well. So, this is the relationship that you should use. Okay. All right. So, last topic for today is this bit level soft decisions. So, we have talked about this soft decisions in one of the previous lectures as well. In soft decisions, what we want to do is, instead of making a hard decision is that the detector decides whether it is 1 or 0. In soft decisions, what you like to do is, you like to preserve these likelihoods, and you tell the detector these likelihoods, and when you convey to this detector these likelihoods, detectors may use this likelihood to improve the error performance. Okay. And we have seen one example of that before. So, detector can also preserve likelihoods at bit levels, okay, and we will see one example of this. So, we are using the gray coding again to assign bits to the symbols, and we want to find out the likelihoods at the bit level. So, detector will like to find what is the probability that bit 1 is 0 given an observation, whatever that observation is. And if you look at this mapping, bit 1 is 0 here and here. So, this probability as same as the probability of signal being S1 and S4. So, this probability is probability of signal being S1 or S4. And what is the probability of signal being S1? This is the a posteriori probability of signal being S1. So, we have to calculate the a posteriori probability of signal being S1. We have calculated these a posteriori probabilities several times, okay, plus a posteriori probability of signal being S4. Okay. You sum up these two a posteriori probabilities, you will get the probability of bit 1 being 0, and from this we can get the log likelihood ratio. Log likelihood ratio is simply log of probability of bit 1 to be 0 divided by probability of bit 1 to be 1. And if you know that probability of bit 1 to be 0 is this, the probability of bit to be 1 is 1 minus probability of bit being 0. Okay. So, once you have calculated this, you can easily calculate the log likelihood ratios. Okay. So, what we are saying is when you have to calculate the probability of bit being 1 or 0, you simply sum up the a posteriori probabilities of the desired signals, and from that sum of a posteriori probabilities you can also calculate easily the log likelihood ratios for bit being 0 and 1. Okay. So, with this we have finished about coherent detection. So far we have been considering coherent detection. We have not considered the case when you have frequency and phase offsets. We have assumed that the receiver knew exactly about the frequency and phase of the carrier. In next lecture we will see what happens when receiver has not complete knowledge about the frequency and phase of the carrier. So, we will learn about detection for non-coherent communication in the next lecture. Thank you.